All right, pooling layers. So a very important topic, especially for all of you who are looking to be the human in the loop. So pooling loops are essential components of convolutional neural networks, and watch the previous video to understand all about what are convolutional neural networks. And pooling layers are commonly used in deep learning for image recognition, CAT scans, X-rays, and processing of these images. Now, let me give you an example. Okay, so imagine that you are trying to describe a busy street scene to someone over the phone, right? So you wouldn't necessarily list every single detail, every single pebble on the road, every brick that you see on the building. You wouldn't do that, right? Instead, you will summarize the important aspects, right? So you will say there is a red car turning around the corner, and a group of people crossing the street, and a tall building in the background. So now, pooling layers in convolutional neural networks (CNNs) do something very similar for images. They basically help the computer summarize information it extracts from an image, focusing on the most important features and discarding the less important ones. For example, if you look over here, this is the original image, and after pooling, it converts it into a smaller feature map or image that basically has all the information that you need to read that image. All right, so what is the real benefit? Why do we actually do this? This helps the computer actually summarize the information that it extracts from the image, focusing on the most important features and discarding all the less important features. Now, this makes the computer's job easier, basically allowing it to process the information faster and become less tedious, or something we call in machine learning called overfit. Now, what is overfitting? Think of it like a student who memorizes every answer for a test, but doesn't actually understand the concepts, right? So just a guy who can memorize everything, doesn't understand anything. So if they get asked the same questions, they will do great on that specific test, but they will struggle when faced with new questions. So similarly, an overfit AI model learns training data really well. If you give it just the training data, it will do really, really well, including anything that may be irrelevant. It may be noise, of course. You know what noise is. Noise is irrelevant material in any situation, right? But this model that overfits, or basically knows its training data really, really well, but cannot do anything else, when it comes to some other piece of information, or it has to read or analyze some other different type of image, perhaps, it struggles to make accurate predictions on all these new unseen images. So this is what is called overfit, and pooling helps prevent against overfit. Okay, imagine that you have a detailed drawing and you want two outcomes, and these both are your different AI models, right? So let's say this is your drawing right over here. You can see it has well defined that this is written business over here. This is a laptop. You can see all the keys. You can see this drawing on this notebook. And so it's very detailed. And you have this calculator right over here. You can see everything, right? However, you want, by pooling, you say, okay, I only need the margins, I only need the broad details, and that's it. I only need the margins, the most conspicuous things. That's all I need to know. And this is what you would get with a type of pooling called max pooling. Okay. And let's say, for example, you said, oh, I don't need the margins. All I need to know is what's the average color in this whole picture? What's the average color? And let's say we have the brown and the white, and we get the, let's say, a light brown color. And this is called your average pooling. All right. So this is giving you an example of what pooling does. And now you can probably see a little bit how this will affect a clinical model. Is this model used to detect, blood vessels, highly circumscribed swellings or organs, or it just gets a regular lay of the land of the image? Let's talk about this a little further. Dear all, I hope you are doing great and that you are liking these lessons and you are enjoying and you are learning. and I did want to suggest something as an option for you. Only if and only if you are one of those who want to have this content in a more organized manner, there is a program that I have set up that you can find in the description. It absolutely is not necessary. However, it is only for those who do thrive in an organized approach, and there just might be a few more goodies there as well. Anyways, I wanted to share this, and now back to the video. Now, as we discussed, there are two main types of pooling: max pooling and average pooling. Now, in max pooling, the computer, your AI, picks up the highest value within that window and uses that as a summary. Like I showed in my hand drawing, as you saw over here, this was max pooling. This is like focusing on the strongest signal or the most prominent features. For example, in a CAT scan, for instance, max pooling might pick up sharp contrast of a tumor, and basically discarding the less significant variations that may be around it. So you can see this example of max pooling, that the tumor is very prominently picked up, and you can see the high definition and the sharpness of all the other anatomical features that you are noticing. Now then you have average pooling, and instead of picking up the highest value, average pooling calculates the average of all the values within that window. And this ends up giving a generalized summary of the information in that area. And for example, in medical imaging, average pooling might be used to understand the overall tissue density. As you can see, the image is not as sharp and the colors are not as prominent. So basically, choosing between max pooling and average pooling, this isn't just a technical detail, this is a clinical decision. So if you are selecting a vendor, perhaps, let's say you choose max pooling, you are telling the vendor and or the program, your AI program, you are telling the AI program that you want to prioritize the most intense features in each part of the image. Now, you are the clinician, and the image has been obtained, and you are telling the computer, it's not that you have to go talk to the radiologist, and you are suspicious, okay, I think this patient probably has a tumor. So you will set your AI to max pooling, and you will say, give me the tumor. I want to find the tumor. That's what I'm looking for. And in the future, you won't be your own radiologist, but the AI will be your radiologist, and you will be adjusting the AI to look for what you want to look for. And then if you choose average pooling, you are telling the AI to consider a more balanced view of the features in that particular image. So you see, in clinical practice in the future, different medical tasks will require different approaches. And sometimes finding the highest signal, like the edge of a tumor, is going to be the most important thing for you at that moment. Other times, understanding the overall tissue pattern is more important, and the choice of the pooling method affects how much detail is kept and what kind of information that the model prioritizes, ultimately influencing the model's ability to diagnose and analyze medical images. Now consider a CNN designed to detect early stage lung cancer on CAT scans. Now, if you have aggressive pooling set up, right? If you have set the AI for aggressive pooling, that might help the model run a little faster, but it might also cause the model to miss many small nodules that are just beginning to form. This is where your clinical expertise becomes absolutely essential. You need to understand the trade-offs inherent in these different pooling strategies and how they actually align with your diagnostic priorities. And you need to know what you're more concerned about. You're concerned about missing, let's say, early disease, or you don't want to overwhelm clinicians by false positives, by picking up every single thing that may not be important. So understanding the right pooling strategy should reflect your clinical priorities. Now let's go over this so that we fully understand this. So pooling layers thus reduce the size of the data while preserving most of the important features and the features that we want, right? We may want different features at different stages or different clinical scenarios. We may want to set our AI for different pooling feature characteristics and see what we need at what time. Think of this as summarizing of a medical image, keeping critical diagnostic information while discarding unnecessary details that we are not looking for. So this makes the models faster, more efficient, prevents overfitting to training data. You can go between high definition to low definition, um, and it helps preserve all the features that you need. And this is critical for medical imaging applications. Then we discuss this image right over here, that we have everything in this image. We don't need everything. We need, let's say we only need the margins, then we will look at this image. Or we only need to know the average color in that image or density, then we will look at this image. Then we discussed regarding max pooling and average pooling. And you saw that max pooling was getting us a more defined image. And average pooling was not giving us such a defined image. Max pooling keeps the strongest signals in each region, ideal for detecting high contrast objects like tumor edges or bone fractures. And sometimes we know we are looking at a CAT scan and we're not able to, even with the CAT scan, tell if the patient has a fracture or not. In the future, we will have these tools, these AI tools, and nowadays we go and change the contrast on these images and change filters. However, in the future, we will have much better tools to pick up fractures or anything else. Then average pooling preserves overall characteristics of each region, which is better for subtle tissue density variations and gradual changes that a tissue may be experiencing. And pooling strategies are not just technical decisions, they are clinical choices, and they directly impact diagnostic capabilities. So you have to balance between model efficiency and diagnostic accuracy, and your clinical expertise should guide architectural decisions. And consider the cost of false positive versus misdiagnosis. This is always important. So, as we say, the most effective healthcare AI system, they are built through collaboration between clinical and technical experts. This was about pooling. Now, in the next video, we will talk about dropout layers.